third talk in this session is from Thang Tran, who is a principal engineer at Andes Technology. Thang is specialized in microarchitecture and design with a lot of experience at Motorola, AMD, Intel, Analog Devices, Centaur, other companies over his career, and he'll be talking about Andy's RISC-V vector design. Thang, go ahead.
All right, my name is Thang Tran, and today I'm going to talk about the Andy vector processor with some technical detail of the microarchitecture. Okay. So I will start with the background information of RISC-V and vector extension, and then diving into the vector processor with overview, microarchitecture, and performance. We do have vector processor with floor plan, tools, hardware, software, co-design. In the last presentation, Kurt Asanovic had talked about RISC-V and the vector extension. I would like to add that Andy is one of the founding members of the RISC-V Foundation back in 2015. And Andy is the first company to announce commercially available RISC-V vector processor. Vector is a co-processor of a RISC-V microprocessor. The Andy V5 microprocessor is used. It is a simple 64-bit 5-stage pipeline. The microprocessor has many options, including when prediction, instruction, data cache, multiply, divide, and of course, VPU and FPU. The load store unit also handle hardware unaligned address and non-blocking cache access for VPU. The VPU including both cache, uncatchable, and custom accesses to external co-processor or local memory. The load store unit allows 16 non-blocking and out-of-order data accesses to external memory, which is good for performance. Important feature of the VPU are the configurable register width, we call VLAN. And this is the terminology that I will use throughout the presentation. And the configurable bus width of 128-bit to 512-bit. VPU is basically is after the retire stage. So the VPUs implement fire and forget protocol, making it simpler in design. The VPU pipeline starting from the vector instruction queue, VIQ, require a couple of pipeline stage to decode and pre-calculating the vector instructions. So all the pipeline stage in the VPU are well utilized. Note that the data access is still speculative, which is important to reduce the load-to-use latency. The ACE instruction, including the custom load store, must still go through the CPU and the VPU pipeline for data dependency checking. We keep the VPU updated with the latest vector extension specs. We started with the RVV version 0.7, and the current version is 1.0. The data format include from 8 to 64-bit for integer and floating point, but we also have a custom data size of bfloat 16 and 4-bit integer. We started with the VLAN and the assembly width at 512-bit, which is the high end of the vector processor. This parameter is very important for performance. The VLAN and the assembly is configurable from 128-bit to 512-bit. And the VLAN to SIMD ratio can be 1:1 or 2:1, which is configurable. The effective VLAN is the programmable by software, and it will be explained later. The number of functional units and chaining provide the most performance impact for vector processor. the lanes, we also implement with multiple lanes, which better for timing and will be shown in later slides. The load store had 3 independent data paths to the vector processor: the data cache, the external memory, and the custom coprocessor and memory. I love this quote from Dijkstra. I have followed the simplicity approach in microprocessor design for over 20 years. Innovative design is important, but innovation with simplicity in mind even more important, and we did this for the VPU. Modular design allows many people to work independently on different functional units. It also allows us to reuse the functional units from the previous design, such as DSP and FPU. Another important aspect is the unit level verification. The local parameters allow the flexibility to modify the timing at the last minute. For example, the floating point mode was 4 cycle latency at the beginning and change to 3 cycle at much later time without impact any RTL modules. We also use Excel in our design with a script to convert the Excel to Verilog case statements. This actually is not new. We used to design with a truth table in Espresso or PLA. The advantages are listed here. One of the examples is the issue state machine for issue micro-ops to multiple cycle. The Excel cases started out with 100 of rows and were later modified to be less than 20 rows without any manual change in the issue RTL logic. And we was able to finish from start to final delivery in 9 months by a small design and verification team. The number of functional units is independent functional units is important. It indicates the maximum number of performance of how many instructions can be executed in parallel. Our VPU can issue 8 micro-ops per clock cycle, which is closer to the maximum number of functional units. The next slide will explain what is micro-op in our VPU. In the context of modular design, the irregular function like pre-ship for 2x and 4x data width and resolve forwarding are done outside of the functional unit. And so the functional unit can execute instruction without stalling. Low is the most important instruction for performance, and we implement low stall to handle. We have many low stall queue to handle 6 independent low stall instruction. So basically 16 instruction can be executed in parallel. The law in RVV 0.8 is broken into 2 instructions in RVV version 1.0. The vector law and extension instruction is broken into 2 instructions. Basically, it's a 2 instruction instead of 1 in the RVV 0.8. And we would provide the load store of the RVV 0.8 at custom instruction. The figure shows 3 independent data paths into the VPU load store unit. We have many independent queues to handle 6 independent load store instructions at one time. The initial design had a bus width of 256 bits, but it is configurable from 128 to 512 bits in later generations. The uncatchable data path is actually out of order. The elmo is the programmable variable which define the width of the operand of the instruction. the width of the operand can be from 1/8 to 8 times the raster width. If the VLAN is 512-bit, then the programmable width of the vector instruction can be 64 to 4096 bits. So if elmo equal to 8, then the operation is on 8 vector registers. Each vector register is basically 1 micro-off. This is the advantage of vector processor over SIMD processor. A single vector instruction is used instead of a SIMD instruction. The number of micro-ops is also dependent on the vector instruction with two X, 4X, and AX data expansion. And so for a 8-entry execution queue, so 8-entry execution queue can hold up to 64 micro-ops per functional unit. Not all functional units have 8-entry execution queue though. The vector instruction are executed after the retire state of the main CPU pipeline. So the instruction are no longer speculative and can write back to the rest file as long as there is no data dependency, which is the innovative in which case we use an innovative rest file scoreboard. Part of the innovation is the future scheduling of the read and write ports of the rest file, so that when the instruction complete execution, the data can be written back to the rest file directly. No temporary register like reorder buffers or register renaming is needed. The temporary register is actually very expensive because VLAN is 512 bits. The vector instructions are totally out of order. Even right after read is possible, which is not even common in out of order microprocessor design. The invention solve all the hazard related to the rest of file read and write port and resource, and schedule the instruction to be executed in the future and complete. So each micro-op check for data dependency independently and available of the functional units, so that chaining happen naturally. The chaining is when the result of the data is forward to the next vector instruction before the first vector instruction is complete. As shown here, when the add instruction is finished in cycle 16, but the other instruction can be started using the data forwarding within of the vector register. And if you look across the instruction vertically, you can see that there are 8 micro-ops being executed at the same time. The VPU include the scalar FPU, which is configurable, and have a NX27V with VPU only, FPU only, or the VPU and FPU combination. And in this case, the vector floating point functional unit are shared. The invention is very flexible. The same innovative algorithms are used for the FPU rest file scoreboard, read and write ports. The resource sharing of the FP functional unit with the VPU. The FPU is also out of order execution and completion. And so simultaneously can issue scalar and vector floating point into the vector execution queue to share the functional unit. And the low store floating point data processed to the vector low store unit. The speed up that's shown here are based on comparison of vector to scalar codes. The speed up is more significant in matrix multiplication, as many more elements can be executed in parallel. Our VPU is 4x the raster and SIMD width of an ARM Neon, and the performance is also better with chaining. our VPU have a custom instruction set as stream import and different data format. The extensible custom instruction set in general give the customer efficient custom hardware accelerators, proprietary and differentiation. The CM55 and Helium is the vector processor. Even our low-end vector processor of VLAN and SIMD width of 128-bit is more powerful. Fujitsu developed an ARM scalable vector processor with the same SIMD width of 512-bit at AMD vector processor. Our numbers are higher in both sustain and peak performance. The number for A64FX is come from the Hot Chip 2016 conference. Here we show that the VPU are designed with 4 lanes. So within the lanes, the data is routed and fall within the lane. So the compute instruction, which is important for clock frequency. So each lane is a 128-bit. So we had a permute logic and the load store will take an extra cycle for routing data across the lanes. This is an overview floor plan for the NX27V, and the FPU is small and embedded within the VPU, and the clock frequency is 1 gigahertz, and the die size is 0.3 millimeter square. We have full tool set of simulator, compiler, assembler, debug for both CPU and VPU. And the clarity is the simulator, and so it supports LLVM, and the clarity is what we call for the cycle accurate simulator, and it provides a virtualizer and analyzer. It provides the pipeline view of the instruction and the functional unit, the resource view corresponding to the instruction uses, star and bubbles within with different color for data dependency. And so this is the pipeline view of the for the instruction, and it will help debug the problem in software ahead of time. And so the overview of the whole trace at the bottom here, and you can actually zoom in to the high or the low performance to see the pipeline view, and with different colors. So this is very powerful tool, and it's available now. So in summary, ND vector processor RISC-V is actually ready for prime time action to enter into the AI or ML application market. So it is the world's first commercial RISC-V vector processor. The 512-bit NX27V vector processor have been shipped to lead customer. Innovative design for out-order VPU and FPU. High performance in HPC and AI application. Flexible VPU configuration to enable wide range of application, and the clarity is used for performance optimization, and NX27Vs is available now to accelerate ML, AI, or IoT application for customer. And this technology will continue to expand the vector product families to meet the requirement of edge to cloud application.
Great, thanks, Thang. We'll have time for some questions. If you'd like to submit a question, please use the Q&A button at the bottom of your window. I've got a couple of questions to start off. Thang, you mentioned that the product is already with a lead customer. Is that production RTL, and when will that be available to general customers?
It is available now.
Okay, a production RTL.
Yes.
Great. Okay. And then you showed a picture of the die layout with the die size. So is that the 128-bit option or larger?
It's a 512.
That's the 512 option.
Yeah, for both the VLAN and the SIMD. Yes.
Oh, wow. Okay. So that's still pretty small.
Yes. We have very efficient design. And
Yes.
so the design, we do both the VPU and FPU out order and all that in 6 months. So it had to be simple, but it's out order.
Good. Always keep things simple, right?
Yes.
So the same question that we had before, is there a 16-bit by 8-bit multiply support in your design?
No, I don't think so. No.
Okay, so I guess if it's not part of the RVV, then it's not supported.
Yes.
And so you mentioned 4-bit integer in-for support. What is that typically used for?
So this is actually in terms of loading the 4-bit integer, and so there's no operation that for 4-bit, but in terms of loading the data, we can load a 4-bit integer, and then do extension to whatever the width of the elements.
Oh, I see. So you can load the 4-bit integer, then you would extend it to like an 8-bit integer, so you could
Yes.
operate on it.
Yes.
Okay, that makes sense. Um, so, um, can you compare your vector processor to the Sci-Fi version in terms of performance and power?
So so in terms of the width, I think we had a 512-bit SIMD, which is twice the size of the Sci-Fi vector processor from Gus and Sanofi. And so in terms of performance, the SIMD width is very important in terms of performance. So most of the performance is based on that. For example, the A64FX, the VLAN is actually 1024-bit, but the SIMD is 512-bit. And we are comparable to that, and we even have better performance in comparison. In terms of power, I think we have one, we design with the 4-level clock gating in our design. And we also do not have any temporary rester. So basically, the area and power is smaller because we don't have any temporary rester. Even the design is out of order. So that's also another point that we believe that we have a really good performance because we actually out of order execution and completion.
Okay, thank you. So in your slides, you mentioned that you had speed ups of up to like 57x compared to running things in scalar mode. I think the 57x number was for a 32 bit floating point matrix multiply. So I mean, I can understand. You certainly get some benefit from the wider SIMD capability, but 57x seems like a lot. Do you know what goes into getting that number so high?
So there are two things. One is because if you look at the you said 32-bit or 16? 16-bit. So there are actually 32 element execute at one time.
Oh, that's what I mean. Okay.
Yeah. So 32 element of 32-bit is, 16-bit is operate at one time. And on top of that, there are chains and then there are out order execution. They would get the performance based on those factors.
Okay, so 32x is just from the data width, the
Yes.
SIMD capability, and then to get up to 57, I mean, then that's almost a factor of 2 from just the overall architecture efficiency.
Yes.
Okay, that makes sense. Question, do you have customers in the AI space, machine learning?
Yes.
Okay. I won't ask you who. The VPU, you can change the width of the VPU. Can you configure it to be integer only?
Yes. Yeah, it can do all the integer and floating point. And so if you only have integer only operation, then you can just send the instruction and you can basically configure out all the floating point units. Yes.
So in the RTL, you could configure out all the floating point units,
Yes.
and presumably that would save die area then.
Yes, a lot.
Yeah, yeah. So I can see why someone might want to do that. Um, so yeah, so you showed the die size number. Do you have any power numbers that go along with that?
Um, yes, but I don't know it right offhand.
Okay. Um, perhaps they can contact you during the breakout session to get that information.
Uh, yeah, I had to ask somebody, so hopefully we can have that number. Yes.
Okay. So, and then is this core able to run Linux?
Um, yes, I think so, but we haven't totally tested that yet. But I believe we can. Yes.
Okay, it has an MMU though, right? So
Yes, it does have an MMU.
so so it should be able to.
Yes.
Okay. So that concludes our session on vector processors. We've heard about 3 new vector processing cores and some very interesting material. So please stay tuned, and we'll see you after the break.